In this video, we're going to take a look at the multiplication of a 3D vector by a scalar value. Now, just like everything else that we've looked at so far in 3D, it's nothing more complicated than a simple extension of the 2D case. So if we had a vector and that vector was v, if this was a 3D vector, meaning we had an x component, a y component, and a z component, and we had some scalar value, so some single numerical value, what we're interested in is what happens if we multiply our vector by that scalar. Now, just as in the 2D case, vector scalar multiplication is commutative, so that means that s times v is the same as v times s. And just as we mentioned in the 2D case, the result is going to be a vector. The number of components in the result is equal to the number of components in the vector that we're multiplying. So our 3D vector has 3 components. That means our resultant vector is going to have 3 components. And just like in the 2D case, it's actually very easy to calculate these components. We're going to see it's no more complicated than an extension of the 2D case where we have a third component in our vector. So if we took s times v, we're going to get s multiplied by our vector, which is x, y, z. And just like in the 2D case, what we're going to do is for the first component of the result vector, we're going to take our scalar and we're going to multiply it by the first component of our vector. So that's going to give us s times x for our first component of the result. For the second component of our result vector, we take our scalar, we're going to multiply it by the second component of our vector, and that's going to give us the second component of our result. So our second component is s times y. And now the only difference from our 2D example is we now have 3 components. So we're going to take our scalar and we're going to multiply that by the third component of our vector to generate the third component of our result. So our third component of our result is s times z. So hopefully you can see there's nothing more complicated there than what we saw in the 2D case. In the 2D case, we'd have had the result as s times x, s times y. In the 3D case, we've simply introduced this third z component. So we simply have a third component in our result, which also gets multiplied by that scalar value. So there's really nothing to it. Well, I'm going to practice just one example here on the whiteboard before continuing. So if I had a vector A, and that vector was equal to, I don't know, 1, 3, and 4, and I had a scalar value which I'm going to call s, and that scalar value was equal to 3, let's say, then s times a is going to be equal to 3 times a, which is equal to 3 times our vector, 1, 3, 4, which is equal to, the first component is going to be 3 times 1. The second component is going to be 3 times 3. And the third component is going to be 3 times 4. That means our result vector is going to be equal to, if I scroll back up a bit, there we go, 3 times 1 we know is 3. 3 times 3 we know is 9. And 3 times 4 is 12. So our result of 3 times a is the vector 3, 9, 12. So it's really simple. It's just the same as we saw in the 2D case. The only difference, again, is that we've got that third component. And we're going to see this occurring a lot in our 3D cases of what we've seen already in 2D. It's just another component, and all of the theories pretty much directly applied to 3D just as they did to 2D. So in a similar way, we saw in 2D that when we multiply a vector by a scalar, we don't change the direction unless that scalar is a negative, but we do change the length of our vector. It's the exact same thing in here in 3D. So the exact same thing we talked about with our scalar. If it's a positive value, then we're going to be changing the length of our vector. If it's a negative value, then we're going to be changing the length of our vector, but we're also going to inverse the direction of our vector, reverse the direction of our vector. It's the exact same thing here in 3D. So everything we discussed about how the scalar value manipulates the graphical representation of our vector and manipulates the actual length and whether the direction is inverted or not is the exact same thing that we saw in 2D, except for our vectors exist in 3D space. That's the only thing that is different. So I'm not going to get into too much detail here because we've covered that in great depth in our 2D video, but I did want to point out that that all still directly applies. The only difference, and it is really the only difference, is that we need to multiply our scalar by our third component. So with that, there's not a huge amount to test here, but I will set just a couple of questions for you to work through on your own. So question 1, I would like you to multiply a vector A, which is equal to 2, 3, 1, let's say, by a scalar, which is 4. So I'd like you to work out S times A, please. So go ahead and work out the answer to this question, and when we come back, I'm going to give the solution here on the whiteboard. Okay, welcome back everyone. So we've got S times A. This is the same as 4 times A, which is the same as 4 times the vector 2, 3, 1, which is equal to the vector 4 times 2 for the first component of the result, 4 times 2, 4 times 3 for the second component of the result, and 4 times 1 for the third component of the result. Fantastic, which gives us a vector that is 4 times 2 is 8, 4 times 3 is 12, and 4 times 1 is 4. Fantastic. So the result you should have got is that our vector for 4 times A is 8, 12, and 4. 8 in X, 12 in Y, and 4 in Z. So that's the first question. And I will bring up a new whiteboard just in case we don't have enough room. I'm going to set another question. So question 2. And in this question, we're going to have a vector B, and let's say that that vector is equal to 5, 0, and -1. Say, and I'm going to have a scalar value, and that scalar is equal to -1. So I'd like you to work out S times B, please. So go ahead and give that an attempt once you have a solution, or if you get stuck, unpause the video and I will work through the answer here on the whiteboard. Okay, welcome back everyone. So we're taking S times B, that means we're taking -1 times B, which is equal to -1 times our vector 5 in X, 0 in Y, -1 in Z. So that's going to give us a vector that has for our first component our scalar, -1 multiplied by the first component of our vector. So that's going to be -1 times 5. For the second component, we're going to take our scalar, -1 multiplied by the second component of our vector. So that's going to give us -1 times 0. And for the third component of our result, we take our scalar and we multiply it by the third component of our vector. So that gives us -1 times -1. Therefore, our resultant vector is going to be -1 times 5 is -5, -1 times 0 is 0, and -1 times -1 is +1. So the result we were looking for is -5 in X, 0 in Y, and 1 in Z. So just to recap, as I hunt down my earlier whiteboard, again, we're dealing with multiplying a 3D vector by a scalar value, and once again, there's nothing more complicated here than what we saw in the 2D case. We simply have an extra component, and because we have an extra component, we have an extra component in our result equal to that scalar value multiplied by our third component. So it's no different to our 2D case, except we have a third component where we multiply our scalar by the Z component of the original vector. And as I mentioned earlier, just as in our 2D case, the effect the scalar value has on the length of our vector and whether or not that vector is reversed in direction is the exact same effect that it had in the 2D case. It's just the same. So we are changing the length of our vector based on that scalar value, and if that scalar value goes negative, then we are going to be reversing the direction of our vector. It's exactly the same as was explained in the 2D vector scalar multiplication, so I'm not going to go into any detail on it here. But with that, that is going to conclude this video. Thanks a lot for watching, everyone.